Let's look at how to apply negative feedback to a current amplifier. Here we have a current amplifier with an input current IN and an output current I out, and a feedback current IF, and under feedback the new source current IS. Notice that we've made the output network negative. And that's something that happens very frequently in these current amplifiers, so I'm just going to start out with a negative feedback network. But with this negative sign and that negative sign together, it makes positive feedback. So in order to compensate for that, what we do is we make the sign of the original amplifier negative, in effect putting our input in the negative terminal instead of the positive terminal. When we do this little operation, the gain after feedback can be seen from this equation here. I out equals minus A, the reason it's minus is because we have that minus, over 1 plus beta times A, and the beta times A is not negative because the minus on the beta and the minus on the A canceled off. And this gives us an inverting amplifier after feedback. So we're going to have an inverting amplifier after feedback, but we can still apply negative feedback with simple beta networks like this, using this block diagram. Let's go see how this would work in a real-life op-amp circuit. So here we have an op-amp circuit, and I'd like to implement the equation that says that I sub I equals I sub S minus I sub F. I'm going to put my I sub I on the negative terminal right here. And I want to make an equation which subtracts off a certain current from that. And the way you make current subtract in real life is to make a node and connect several wires there. So I'm going to make this current coming in here, I'm going to make that equal to I sub S, and I'm going to make the current going down here equal to I sub F. And in this situation, Kirchhoff current law at this node tells you that II equals IS minus IF, which is the equation we wanted. Now I'm going to also connect the positive input to ground so there's a place for the current to flow. And on this op-amp, the output current comes out here. And on any op-amp or any amplifier, you have to have a load resistor. So I'm going to connect the load resistor on here like this. And the current going through that load resistor is I sub out. That's the definition of a current amplifier. It puts a current through your load resistor of a certain amount. Now, what we would normally do is we would normally connect the output of this load resistor, the end, the bottom end, to ground. But remember, we need to make a network that samples a little bit of this output current and turns it into this I sub F over here. So I'm going to put my sampling network between this point right here and ground, which is going to go down here. And that sampling network needs to take just a piece of that current that's coming through the load resistor and make it into I sub F. So to me, the easiest way to do that is to make a current divider. So let's just connect a current divider on here. And I also have to have the other resistor, which is in parallel. And I'll call that R2. And that resistor needs to send a current into I sub F. So I'll just run it over here and put it into I sub F. But it also needs to have the same voltage across it as R1 here. In other words, it also needs to go to ground. Now, fortunately, that happens in this situation because, remember, we now have negative feedback through this R2 resistor, which makes the resistance, the voltage at the negative terminal, the inverting terminal here, the same as the voltage at the positive terminal, which we connected to ground. So that works. When you're connecting a sampling network for current, they call this current sampling, you need to connect it on just like you would an ammeter. Your ammeter has to have the same current flowing through it as the that you're trying to measure. In our case, we're trying to measure the output current here, and our circuit right down here, this one with R1 and R2, has the same current as I out flowing in it, and the part going through R2 is turned into actually minus IF. If you notice here, the current going this direction right here to the left is minus I sub F. And we can write an expression for that over here. Minus I sub F equals R1 over R1 plus R2 times I out, or I sub F equals minus R1 over R1 plus R. Oh me, what happened there? Undo. Undo. Plus R sub 2 times I out. So this expression right here is beta. It's actually minus the beta. The same minus beta that we had up here. Notice it's negative. I'm assuming this whole quantity in the thing here is negative because I'm feeding into the negative terminal here. And it turns out to be that way because the resistors are positive. So we've in effect created with our circuit the same diagram for this circuit is given up above, the diagram we started with. So that's how you implement current feedback on an operational amplifier, and this is called parallel current. Parallel current feedback. It's parallel because the input has to be parallel. Notice these input things are in parallel here. In other words, the source right here, which comes in, putting in IS, is in parallel with the input current and the feedback current there. So that's how you do parallel current feedback to make a negative feedback on an operational amplifier.